on, and we're going to jump right in. So welcome. Thank you so much for showing up for our fourth 10 in 10. GPM stands for Global Precipitation Measurement Mission. These are our celebrating our 10 years and counting anniversary. And so what I have done as the outreach coordinator is I have pulled together some I think super people who will be giving presentations through November on the second Thursday of every month at 8 p.m. Eastern time. And we're coming together to share, and then hopefully you will propagate this and share this out as well. Some of just the amazing things that not just GPM mission, but other missions as well are doing to help us better understand and protect our home planet, as well as showing you some of the tendrils, some of the networks and ways in which lots of different groups, some related to NASA and some not, are taking this information and are sharing it out. So we do hope when you get a chance, you will, and I'll put our website in a couple minutes when I'm not talking, but I'll put the website in. And if you've missed any of our webinars, you just go to the story map resource packet that I've put on each of the pages, and you can see the webinar and you can see all the different resources that we have collated and put together for your learning pleasure. So without further ado, here's how this is going to go tonight. I am going to introduce our four phenomenal speakers, and then they're going to present one at a time. After they present, if they have a little time, they'll answer questions. Most likely, they'll look for your questions in the chat and they'll respond to them. Please make sure your questions are related to the topics that we're talking about. And so then at the very end, I will share a little bit of this resource packet that I've put together if we have time. If not, you have access to it, and I hope that you'll enjoy it and share it widely. So let me tell you a little bit about these folks. When you go to the story map, you will get to see their bios in full at the website that we created to advertise this event. If I were to go through their entire bios, it would probably take all evening, because these are four absolutely phenomenal, incredibly talented folks. So we're going to start off with Dr. J. Marshall Shepard. He's the leading international weather and climate expert and is the Georgia Athletic Association Distinguished Professor of Geography and Atmospheric Sciences at the University of Georgia. He was the 2013 president of the American Meteorological Society, there's a word for you, and he serves as the director of the University of Georgia's Atmospheric Sciences Program, the associate director of climate and outreach for the Institute of Resilient Infrastructure Systems, and is a full professor in the Department of Geography. His areas of research include urban climate, hydrometeorological extremes, weather climate risk, and innovative outreach strategies. Now, another thing that's so super cool about Dr. Shepard is he spent 12 years as a research meteorologist at NASA, and he was the deputy project scientist for the Global Precipitation Measurement Mission. After Dr. Shepard, Andrea Portier, who is my colleague, she works at NASA Goddard Space Flight Center, and she serves as the application lead and coordinator for the Global Precipitation Measurement Mission and for the Atmosphere Observing System. And in these roles, what she does is she engages with different stakeholder communities to help them understand and quantify how NASA satellite products are applied for decision making. Then we're going to have Kasha Patel. She is the deputy weather editor for the Capitol Weather Gang at the Washington Post, covering weather, climate change, and the environment. Before joining the Post, she was with us at NASA at Goddard Space Flight Center and worked for the GPM mission on our outreach team. And then she will be followed by Dr. Genevieve de Messier, and she is the lead for the Earth to Sky Interagency Partnership. And you're going to be learning a lot more about this partnership. She's based at NASA's Goddard Space Flight Center, and she lives nearby with her wife, her dog, and 3 cats. And before coming to NASA, she earned her PhD from the University of Virginia and managed the astronomy education program at the Smithsonian Natural Air and History Museum. So without further ado, let's go forward and start with Dr. Marshall Shepard.
Well, thank you, Dorian. It's really kind of a full circle moment here to be speaking with you about the GPM mission, Global Precipitation Measurement. It's certainly a significant part of my career and one that I reflect fondly upon during my 12 years as a scientist at NASA. And I still utilize GPM data and GPM resources in my research to this day, even at the University of Georgia. And so I'll take a moment to share my screen and we'll dive right in. Okay, so hopefully you can see my screen. You should see a white screen
Looking
with some
great, looking
purple and
good.
blue. And so I entitled the talk Dr. Marshall Shepard and the GPM Legacy. So we're celebrating the 10th anniversary of the GPM mission. And I know that there are a series of talks scheduled throughout the year, all the way into the fall. So it's an honor to be asked to be a part of this. And so I'll spend about 20 minutes talking to you from multiple perspectives when it comes to the GPM mission, what it means to my career, and what it means to the planet. And hopefully that will stimulate a few questions for you along the way. So I have to start with sort of this picture of a honeybee because people always ask me how I got into the field of meteorology. I am a card-carrying research meteorologist. As you heard from Dorian, I was the president of the American Meteorological Society, which is the largest professional society in our field. But it didn't always start that way. I always tell this story because it's relevant that you will have different pathways in life. I wanted to be an entomologist when I was about fourth or fifth grade. I used to be out in the yard. I was an only child, so I spent a lot of my time on those hot spring and summer days here in Georgia catching insects and putting them in jars and watching what happens to them. And along the way, I got stung by a honeybee and learned that I was highly allergic to bee stings. And this was before everyone carried an EpiPen around. Candidly, I still don't carry one around. But I decided that I probably shouldn't do a science project on honeybees for sixth grade. So I switched over to weather. And, my mom was a single parent teacher. We didn't have a ton of money around. So weather stations were very expensive. So I decided to make weather instruments from things we had around the house and take measurements with them and design a little weather model for my little community there in Canton, Georgia. And so that's how I came to study weather. I really became interested in weather, but I didn't want to forecast the weather. I was more interested in the hows and why of weather. And so went on to Florida State University, got a bachelor's, master's, and PhD in meteorology. And interestingly enough, there's a strange connection between Florida State and how I ended up working on the GPM mission at NASA, but I'll circle back to that in a moment. In fact, right now. So these pictures that you see represent key figures in my career pathway at NASA and into the GPM program. First, you see on the top right is Dr. Warren Washington, who is on my Mount Rushmore of career influences. He's one of my mentors. He's a recipient of the Presidential Medal of Science, which is the highest award a U.S. citizen can receive from the president. And he has just been a significant guidepost along the way in my career. So when I was a young graduate student coming out of Florida State, I knew that I wanted to work at NASA. And so my doctoral advisor, Dr. Peter Ray, uh, reached out to Franco Einaudi, who you see there on the top left. Franco was the director of the Laboratory for Atmospheres at NASA Goddard Space Flight Center. And so Peter called Franco and said, this guy, he's really, passionate about what he does. He wants to work for NASA one day. It's his dream job. So they flew me up. I went up to NASA, did an interview. They liked me, but there was a hiring freeze in the federal government at the time. And so Franco said, well, here's what we'll do. We have different contractors. Why don't you go work for this company called SSAI? It's a contractor to NASA. And as soon as the hiring freeze is lifted, we'll try to find a way to hire you. And lo and behold, that did happen. I got hired as a support scientist at NASA. I was very junior, only at that time, only had my master's degree. And I worked for a guy right there on the left, Bob Adler, and also got to work with Joanne Simpson, who at that time was the TRIM project scientist, the first woman to receive a PhD in the field of meteorology, a legend in her own right in the field of meteorology. But I found out about this program that NASA offered that allowed you to go back and do your PhD. So I applied for it, got accepted, went back to Florida State University and did my PhD, or at least started the program. And at that time, Dr. Eric Smith, who you see in the glasses there, uh, was one of my professors. He was on my PhD committee. He was a professor at Florida State. Along the way, Dr. Chris Kumaro became the TRIM project scientist, and I came back to NASA. I was working somewhere in that process as the TRIM mission, which I'll talk about in a moment, was winding down. It was decided that we needed a follow-on mission to the TRIM mission. So the foundation for my entry into the GPM came through my connection to Dr. Eric Smith, because Eric Smith ultimately would join NASA as the GPM project scientist. But before we go there, let's talk a little bit about TRIM. Now, the Tropical Rainfall Measuring Mission, or TRIM, was a very unique satellite. It was a joint partnership with the Japanese Space Agency. Here you see it before you. It had 5 instruments aboard, one of which was very unique. It was the first time that anyone had flown a radar in space. And so this satellite was going to be a unique prototype for precipitation measurement for years to come. We started it in the tropics. Joanne Simpson, who was one of the visionaries of this mission, said, we want to measure tropical rainfall between about 38 degrees north and 36 degrees south, because if we know anything about rainfall in the climate system, much of the energy release from rainfall and cloud formation in the tropics drives or helps drive some of the global circulation patterns that affect our weather around the planet. And so this instrument, the precipitation radar, was a first of its kind. It was designed and built by the Japanese Space Agency, JAXA. It also flew a microwave imager, a typical visible instrument, and a lightning sensor. So as a young scientist at NASA, I cut my teeth on the TRIM mission. I was supporting people like Jerry Heimsfield and Bob Adler and Chris Kumaro, and really serving as a junior scientist. And along the way, I had this really interesting idea, because the TRIM satellite was starting to produce data. And I was always interested. I'd read a few scholarly papers about this idea that cities can cause their own rainfall or enhance existing rainstorms because of the heat that they produce, or perhaps because of the pollution in cities. And so one of the criticisms of previous research in that space had been that, people had only looked at one city at a time. It was anecdotal. They put all of these instruments around one city like St. Louis and drew all of these conclusions based on one field experiment for one city. Well, I said, well, you know what? We've got this satellite that can now measure precipitation from space. So I could look at many different cities at one time and sort of mitigate that weakness of some of those studies. And so I published a paper looking at whether we could detect rainfall patterns and urban effects on rainfall in the TRIM data. And we did. We found supporting evidence that over and downwind of major cities in the summertime, there was more rainfall, likely because of this urban effect that you see diagrammed in this little schematic that I published in that paper. On the right is a more recent study that we've done for Atlanta. This is the Atlanta area here. By the way, I'm talking to you from right about there. Downtown Atlanta is here. This is Gwinnett County, and I'm sitting right about there in that anomaly region. So we know that over and downwind of Atlanta, we tend to see more rainfall. And there's some complexities to why that happens. But the greater point to that is that much of my early research was born from those studies, and I've gone on to continue to publish papers in that space, have been recognized by the President of the United States with a P-Case Award at the White House and election to the National Academies based on some of this work. Now, at that time, this was the fleet of Earth observing satellites in space that NASA had launched. It was really a glory day for Earth science measurements in the NASA Earth Sciences program. You had the TRIM mission, you had Landsat 7 and QuickScat, which is a measuring ocean processes. You had URs and GRACE. It was just a glory day of this time period. I started sort of thinking about other ways that we could apply this rainfall data that we had from space. So, at this time, we knew climate change was becoming a problem. I was increasingly interested in whether hurricanes were producing more rainfall because of climate change. In other words, as climate is changing, are hurricanes becoming wetter? Are they producing more rainfall, which would ultimately lead to more flooding? But before we can answer that question, I needed to establish a baseline to what types of tropical cyclones produce what types of rainfall. So I published a study with colleagues in 2007 looking at using the TRIM rainfall data to characterize or quantify how much rain is being produced by Cat 1, Cat 2, Cat 3, Cat 4, and Cat 5 hurricanes, tropical depressions, and so forth. And what we found in that study is that from a flooding standpoint, it's actually the weaker storms, the tropical depressions and slow moving tropical storms that are the most significant rainfall storms. We saw that in 2017 with Hurricane Harvey, for example, in Houston. Hurricane Harvey produced a significant amount of rainfall, up to 40, 50 inches of rainfall, mostly when it had decayed to a tropical storm that was stalled over southeast Texas. So this was another sort of way that I was applying TRIM data. But then somewhere along the way, we realized, okay, we've demonstrated that we can measure rainfall from space using this technology. Let's do it globally. And so at that time, I had come on board. Eric Smith was the project scientist. He had invited me to be his deputy project scientist. And we started making the case to Congress and to the decision makers at NASA for why we needed this global precipitation measurement mission. And you can see one of the early slides that I used to use in my role as the GPM deputy project scientist. I would make this point that we have this water cycle that everyone learned about in fourth grade, but most of the fresh water is locked away in glaciers and ice cover and so forth. Most of the Earth's water, in fact, 97.5% of it is salt water. We can't use that. So we live off about 2.5% total fresh water on the planet. And frankly, most of that is locked away. So our drinking supply is very much dependent on a very tiny fraction of the available fresh water on the planet. And as you see on the right, stress is apparent. So we were making this case for why we needed to measure global precipitation. It will feed into our weather models. It will help us detect trends for climate change. It will help with flash flood prediction, agricultural prediction, and so much more. So that was the sort of basis for my discussion. This is another really interesting set of slides that I used when we were making the case for GPM. What you see here are, at that time, all of the ground station rainfall gauges on the land. Now, one of the things that you should astutely see is that most of the planet is water. So we can't put rain gauges out there. And then even where we have rain gauges over land, it's very sparsely covered. And so I said, imagine what the typical diameter of a rain gauge is. If we add those typical diameters up and put them together, it ends up being about the surface area of a couple of basketball courts. So I made the case that in terms of solid measurements of precipitation on the land, which is only about, less than 30% of the land cover of the planet, we only have about a basketball court or two's coverage of rainfall. So we needed this global satellite mission. And so here you see one of our original slides. I dug it out. This is history before you, and perhaps some of you've seen something similar if you've been in this lecture series. This is one of the original slides that we used in the program to define the scientific objectives for GPM. We said through more accurate 3-hourly global high resolution precipitation measurements, we can produce accurate renditions of the water cycle. establish quantitative relationships between water cycle change and climate change, improve short to medium range weather forecasting, and enable a host of improved hydrological applications from floods, drought to crop conditions. We couldn't do it with one satellite to get global coverage. Ideally, we'd put these instruments on a geosynchronous satellite, which is staring at the same locations. But because of the power and mass requirements of these particular instruments, we can't put them on a geosynchronous satellite, which is flying at about 35,000 kilometers above the planet. So we have to use a constellation approach. So we have a GPM core satellite that has a dual frequency. It has two frequency radar. And then we use these little constellation of satellites carrying microwave instruments. And so they're zooming around in their little constellation, and that GPM core, wherever it has coincident measurements with those constellation members, which are less accurate, the GPM core satellite, which has a very accurate suite of instruments, can calibrate these less accurate measurements from the constellation. So that in a nutshell is the concept of GPM. But the mission itself was not just the satellites. It was also a series of ground validation sites. It was a very complex data processing system and so forth. So that is in essence how you design a satellite mission. You work with engineers, they build it, we launch it, and then we start getting data. And here is an example of some of my scholarly research with my former PhD student, Dr. Teresa Anderson. I'm going to see if we can play this. We came up with this concept of the brown ocean effect, this idea that hurricanes oftentimes don't weaken when they move over land. If the soil is sufficiently wet from previous weeks of rainfall, you actually can get maintenance or intensification of tropical cyclones, and we call that the brown ocean effect. So I'm going to show you an example using data from a GPM iMerge product. So what you see here, this is a tropical storm Bill, but Bill hasn't formed yet. But what you see is this is rainfall. I want you to keep an eye on Texas because Texas is going to see a lot of rainfall. See that rain? Watch what happens to the soil moisture as all of that rain moves through in the previous week. It goes from red to blue because of all of that rain. So now the soil is very moist. Here comes Tropical Storm Bill. Bill moves over this very moistened Texas and didn't weaken. In fact, it intensified. See how it still looks like a hurricane or a tropical cyclone? That's exemplary of the brown ocean effect. Hurricanes aren't intelligent. They don't necessarily know they're not still over the ocean if the wet soil is there. So what you saw is a combination of iMerge GPM-based rainfall data, soil moisture data, and cloud data that we could use to sort of study this brown ocean effect. So the so what for all of this is that we are living in an era of climate change. A person born in 2020 will experience more climate hazards during their lifetime on average than a person born in 1965. So this is data directly from the National Climate Assessment Report, and it just illustrates that we are a part of what I call a new normal in terms of climate hazards. This is the significant climate events that happened in 2023. And you can see that all over the world, there were significant hydroclimate, hydrometeorological events ranging from hurricanes to atmospheric river events, cyclones in the Indian Ocean, typhoons in the Pacific, and so forth. And so the GPM satellite mission contextually provides a climate context to study how some of these water-laden extreme events are changing. So this is a picture of me sitting before the House Science Committee in Congress in 2019. And I told them something very clear. Extremes are becoming more extreme, and people and infrastructure and the economy and so forth feel extremes more than average. And so we have evidence that that's happening in this. I'm just trying to paint a picture of why GPM continues to be relevant. This is data from the National Climate Assessment that shows that the heaviest precipitation events have increased in the last 50 or so years. In other words, when it's raining with greater intensity, It's raining harder in almost every region of the country. Here in the Southeast, 37% so. So precipitation events, the severity and frequency of heavy precipitation events, is we're living in that era. Because of that, we're seeing elevated losses in dollars for flood risk. We're seeing annualized changes projected over the years 2020 to 2050. So extreme precipitation is a challenge for us, and the GPM satellite and its mission continue to provide data to help assess flood situations like you see here with Hurricane Harvey or Hurricane Ida in this case. And I'm going to end with some points that sort of have been sort of reflective of how some of my research has pivoted. This is Hurricane Ida, made landfall in the Gulf of Mexico a few years ago. Produced flooding in a neighborhood like that, produced flooding in a neighborhood like that. This neighborhood has greater capacity and resiliency because it's a more fluid neighborhood. So even though they're exposed to the flooding, they are less vulnerable than this community who has lower socioeconomic capacity. So they have higher vulnerability and less capacity to bounce back. And so these days, I'm thinking about much of my research from this risk framework, which captures the fact that we have these increased hazards, whether they be hurricanes, heat waves, or floods, who's exposed to them, how vulnerable they are, and then how much ability they have to bounce back. So as we think going forward about climate and weather extremes, we've got to think about some of this perspective. So I want to stop there because I'm itching to hear from some of the other panelists. I've got a little time that I can stick around, but I would advise if you do have questions, please drop them in the chat because I will not be able to stay for the full discussion tonight. But it is important for scientists like me to engage broadly. That's why I'm speaking with you tonight. That's why I host the Weather Geeks podcast for the Weather Channel, write for Forbes and so forth. So thank you so much for your attention tonight.
Wow, thank you so much, Marshall. Just I'm a fangirl, so I got a fangirl all over here. Used to be a long time ago when I was a classroom teacher. The beginning of the textbook that I had focused on Dr. Shepherd, and this was even before I worked for GPM. And I had made that was always the initial task for all of my students, was to read this information and learn about him and the work he did, and get excited about all these amazing opportunities in the future, and the way you can go from just being interested in catching bugs, to then gracious, working for NASA, working with a satellite mission that's just trying to figure things out and measure precipitation. And wait till you hear what Andrea is going to tell us next, how we're taking these data and we're feeding them into climate models. So I'll continue to put the story map information in the chat while Andrea is presenting, and you will be able to find lots and lots of resources and information related to everything that you're hearing tonight. All right, it's all yours, girlfriend, and you're looking good.
Thanks, Dorian and Dr. Shepherd. That was an amazing talk. I'm excited to, build off your talk. I think this is very timely. Thank you, everyone, for taking the time to be here at this webinar today. I'll be really focusing on exactly how we can use NASA data, such as GPM, into climate models to help us build climate resilience against many of those extreme events that people are facing throughout the world. So climate modeling, Personally, I think it can be a very complex topic that can be talked for several hours, several days. But in reality, what I want to do is just cover the basics of what climate modeling is. And I hope that after my talk, I only have about 10 minutes of time. And so I'm looking at that time, is that I hope when you walk away from my presentation, you can understand and learn about three things. One is, why is climate modeling important? Two, where does NASA come into play, especially GPM, in terms of developing and improving climate models? And then three, how can these climate models support actions around you, around all of us? So I really do hope you enjoy this talk. I encourage questions in the chat, and we can talk about those at the end of the webinar. Okay, so Dr. Shepherd already alluded to this, but I just want to remind you all that when we talk about climate, we're talking about, an area's typical weather conditions, often 30 years or more. So why is this important? And again, what I want to emphasize here is that I'm giving you an example just of the US, is that in 23 alone, the US faced over 28 weather and climate related disaster events, and it cost the US over $93 billion. Now, these costs are only going to grow. These types of events are only going to continue. So we need to understand how we can be better prepared for these events and also to build resilience. And so how can we start to play a role in understanding these events going forward? And that's where climate modeling comes into play. Climate modeling is one of the only ways we can see the future and the impact of our actions, especially in terms of policy choices that we make today. Climate models provide the information needed to help build climate resilience. A couple examples I have on the screen are such as it helps us improve forecasting of fire seasons. It helps us better understand the changing impacts of hurricanes. All of these can help us in turn understand more about crop resistance, crop production and resilience, to even how to improve infrastructure across coastal areas. So as I keep on saying the term climate model, let's really break this down. What exactly is a climate model? And I'll kind of talk about this very broadly, is that essentially a climate model is a computer program that helps understand and mimic our Earth system processes. And it really ultimately helps us predict future climate patterns. How we can visualize what a climate model is, it's made up actually of a number of mathematical equations describing the physical and chemical relationships among Earth systems. So those physical and chemical relationships in the atmosphere's interaction with land, ocean, and sea ice, all of that. However, there's not just one mathematical equation that represents the Earth. The Earth is a very complex system. And so what many of these climate models do is that they divide the Earth, or even let's say the atmosphere, into a 3D grid. And now each grid has their own mathematical equation to represent the environmental processes that are going on in that specific area. So let's say you have a mountainous terrain. It's representing the atmospheric and land conditions of that mountain area versus, let's say, over ocean will be different. And so all of them have different mathematical equations that help explain those physical and chemical processes. Why is this really important? Well, this helps us simulate experiments that we cannot do in the real world. Take, for example, let's say if we wanted to project how much CO2 would impact a certain area. So we insert amount of CO2 projections into our climate model, and we see the effects in long term. Let's say we want to see the impact of a volcanic eruption. We can understand the impact of, let's say, carbon dioxide or sulfur dioxide that's emitted from volcanic eruptions. And we can see those impacts through climate modeling. Okay, so where does NASA come into play? Well, NASA is a leader in making space-based measurements of climate variables, from precipitation, water vapor, and temperature. This image or this video that you see on the right is really depicting what NASA has. It has over 24 satellite missions that are measuring the pulse of the planet and really understanding Earth as a system of systems. And so NASA collects data in real time, but also has started collecting data for a long time. Some of the data is from anywhere from 5, 10, 15, 20, or even 50 years of data collection. That's a long time collection. And all of that data, from even real time to past data, are used to help support climate models. So I'm not going to play this video just because of timing, but this video, it's called How NASA Satellites Help Model the Future of Climate. It's a fantastic video that was made at NASA, and this is all part of the packet that Dorian's been posting in the chat. So please, I encourage you to all look at this and enjoy this video. Okay, so now, I talked about a little bit and gave you an overview of climate models, a little bit where NASA, why we have all this fantastic data, but how does it actually help build and develop these climate models? I want to cover 3 ways, primarily how NASA data and especially GPM data is used to build climate models. The first one is model parameterization. As I mentioned, NASA is continuously measuring the pulse of the planet. So measuring variables like precipitation, temperature, water vapor, wind, ocean health, a number of things. All of those, the more measurements we have, the more understanding we gather about Earth's system processes and the relationships across these processes from the atmosphere, land, ocean, and sea ice. As we gather more of this data, it provides us more information to develop and build those mathematical equations, make better mathematical equations that create those climate models. So that's one, model parameterization. The second one is data assimilation. Essentially what they're saying is that they're using that real-time data, so that data that we're collecting right now and setting the initial conditions of a climate model to start a climate model running. Why is that important? Well, if we're taking real-time data, we're really representing what is going on Earth, or let's say in the atmosphere at that present moment. It's better to use data of today versus, let's say, of the past like 30 years, because we're closer to the time that we need to project data, but also we're understanding more about the system as of now. The last one is validation, and some people might use the word hindcasting for this as well. Validation is critical. In order for us to evaluate the accuracy of a climate model, because none of us can necessarily predict the future and be 100% correct, but what we can do is check the accuracy of these climate models. And so what validation comes into is using real world observations, such as data collected from NASA, from GPM, to check the climate model's accuracy, meaning check the past observations to determine the accuracy of the model. So what I want to do with the time that I have, I only have a minute or so, is that really walk you through the validation. Where GPM, because this is in celebration of GPM, how is GPM supporting climate modeling activities? And as I mentioned, its validation is a significant component. GPM, along with TRIM, has been around for over 24 plus years. That's 24 years of data that we can use to help see how well a climate model behaves. And so what I want to do is just give you a high-level overview of what I'm talking about. At NASA GIS, a center in New York, is that they develop these climate models. They need to test these climate models. So what you see in this plot is actually them checking their climate model from June and July of 2014 against real observations that GPM made. If you look in the top quadrant of January, you'll notice is that it's slightly different from the bottom left quadrant if you look at South America. What I really want you to focus on is that it really underestimates precipitation. That model underestimates it of what was actually observed. When you look at July, the climate model overestimates precipitation in the Western Pacific, but really doesn't highlight much precipitation across South America if you look in the south or in the right bottom quadrant. What I'm getting at is because the models don't match up to observations, those climate modelers need to go back, tweak their mathematical equations to improve them to make the models better. And so I think I'm a little bit out of time. And so what I want to do is end with something like this, is that I live really close to the Chesapeake Bay. It's about 30 minutes east of Washington, D.C. NASA observations like GPM can provide us a very comprehensive view of what's going on in the area of our interest. And having a lot of NASA data, it can help us have a view of the Chesapeake Bay ecosystem. Now, all of that data is input into models, which help us, especially for the Bay, predict how the Bay will respond to future conditions such as pollutant loads, land use changes, or even climate change. Now, how those understandings from those models are used by decision makers at all levels to determine how to best to restore and protect the Bay. So I will end there because I think my time is up. And I hope you all learned a little bit about climate modeling and how climate modeling is important and where NASA comes into play. Thank you so much, Dorian, for having me on here. I really do appreciate it.
It is a joy and a pleasure. Thank you so much. It is really, really neat to have Dr. Shepard, who, as he said, cut his teeth at NASA and, you know, is doing these amazing things now. Have our Andrea Portier, who is currently working at NASA and doing absolutely amazing things. And next, we're going to be pivoting over to a former member of our GPM outreach team, who now is also going on and doing some really crazy, amazing things. Not only is she a writer for the Washington Post, which I read every day religiously, the paper copy, my children tease me, but she also is a pretty incredible stand-up comedian. So with that, I give you Kasha Patel.
Hello, thank you so much. This has been such an informative seminar, and also a lot of throwbacks. You know, when I was at NASA, you know, I started out as an intern and I worked on the GPM satellite. And, you know, as a young person, you just get thrown into this world with all this Earth observation data, and it's incredible. I have been at the Washington Post now for almost 3 years. I am part of the weather coverage, and I will share my screen and I will tell you a little bit about what we do on a day-to-day basis of weather coverage, and also how we link it to climate change. So when I started there, I was part of a great team called Capital Weather Gang, and we are known, if you're in the DC area, it's fun, you know, and accurate. You know, we try and be as accurate as we can to tell you what the weather's going to be like in the DC area, as what we also did national and international news. In the past year or so, the Washington Post has invested a lot of resources into growing their climate department. This is today's climate department, what we publish in the climate department. And it's so many different things. I mean, we have different categories, right? From, you know, the effects of climate change to climate solutions to special graphics projects just about climate change. And then we also have the weather department, which I'm in. You know, when I was at NASA, it was a great boot camp to learn all you can about how we observe Earth. I talked about a lot of environmental changes that are more like land use changes caused by humans, disruptions to the environment, as well as climate change, as well as just weather that wasn't connected to climate change necessarily. It was just literally showing the data of the weather that happened. When I came here at the Washington Post, I think I really became enamored with weather, because it's incredible how many people care about it. You can't go out with your day without checking the weather, right? Whenever we would have rainfall, storm, a surprise thunderstorm in the middle of the night, and all the dogs would get up and, you know, start howling and stuff, we would hear about it on social media the next day. And I also managed the Capital Weather Gang social media, and we would get so many more follows, so many more comments in those few moments. The weather team, we are the most read of the climate section because we produce so many things and everyone needs to know this information. I'll take you through a couple of articles that I have done, as well as other unique ways that we try to tell you about this information, which sometimes can be hard to swallow. This is kind of an interesting, I love that this is GPM seminar, because rainfall is, if you have to tell me, like, if I could only pick 1 to 2 data sets about Earth and to see how Earth is doing and have to gauge how everything else is going, like rainfall would be up there, right? Rainfall is a critical part of how our Earth system works. And it's also a critical part of what we visualize. We have so many different sources. This one is at a slightly higher resolution. So this one isn't necessarily, this one isn't GPM data, but GPM data can also help us see these same trends. This article was from September 2022. We had this crazy summer of where there was a lot of rain, all these crazy 1,000-year floods over all these really drought-stricken areas. So we just kind of mapped out so everyone could see, like, what was actually going on that summer. And then the article, we explained that. The precipitation data is also really great because it comes in so quickly. I mean, GPM, you can get it almost real time practically with the constellation. That kind of near real time data is really helpful when you do, I mean, I'm in the news world, right? So we respond to things as they happen. So, you know, this is a very common thing that we repeat every time there's an atmospheric river, a big rain event coming over in the East Coast or the West Coast of the United States, you know, from Pacific Northwest to California. It can cause a terrible amount of flooding. We can always show that with precipitation or water vapor, whatever it might be. Now, it's one thing to talk about weather in isolation, saying, hey, this weather event happened. And you can talk about why that weather event happened from the systems on Earth that have formed to drop the rain in such a way. But increasingly, we have to talk about underlying factors that are exacerbating those systems that are in place. And that would be climate change. So more and more, when we write these news articles, we do have to connect it, if appropriate, to climate change. We write entire articles, oh, how climate change is making atmospheric rivers worse. The atmospheric river that I just showed you. Studies, we highlight studies that show, oh, climate change is bringing more intense rain to the US. I mean, these are stuff that the science has gotten so specific that they can actually attribute certain events or even certain seasons to stuff. I mean, this is also another one, hurricane season. Hurricane season has so many different factors, a hurricane that causes a hurricane to strengthen, and climate change from how strong it can be to also how much rainfall it can put down, and climate change can be a part of that as well, as we see in formal studies. It's not just all about rain, just to give you an idea of what exactly we all do. I mean, it's not just rain, it's also drought and heat domes and heat waves. And this is one of our articles, and I like this because we also have some visuals with it that help you understand that. In terms of things that I think are maybe the most counterintuitive for the public to understand is, you know, going back to my first example, you have this map, you see that a lot of drought-stricken areas experience a lot of record rain. And then we have scientists saying, hey, this is actually climate change. And I think it's kind of counterintuitive for a person to think, oh, how can climate change both be making something drier and also wetter, and sometimes even in the same area? And to wrap your head around that, it is confusing. So we often write, that's a very fine point, and we wrote an entire article about it. We will continue writing entire articles about it, but you know, essentially a warmer atmosphere can hold more water in the vapor phase. So that means there's more rain that it can hold. So when it comes down, there's more there. But at the same time, it's also drying out the land because it's sucking up all of that water. And that makes it even worse because then the land gets very dry and it becomes very, very solid. So when the rain does come down all at once, it's more likely to flood. This is obviously, you know, becoming more and more important with projections, IPCC report. I don't have a ton of time, but so this is obviously a lot to swallow, right? Because we're talking about, you know, extreme weather, I think, is one of the most concrete effects of climate change that we experience in our lives. You know, it's becoming every single year, there's an event that affects our lives, affects our homes, and that is going to be tied to extreme weather exacerbated by climate change. So it's not exactly a happy topic. And how do you communicate that in a way that people understand? Well, not to make light of it, but we have tried a few different methods. Oh, you know what? I think I did not. Let me stop here real quick and reshare because I need to click share down. All right, I just have a couple of videos that hopefully won't take long. This is a fun video.
Heat waves are going to get a lot worse as global temperatures rise. But how much worse? Let's take a look. Dave, we'll see events that used to occur on average once every 50 years increase in frequency and intensity. Today, heat waves are 5 times more likely to occur than they did in the pre-industrial era. At 1.5 degrees Celsius, heat waves will be 9 times more likely and 2 degrees hotter. Nope, sorry, you're also going through a drought. At 2 degrees Celsius, 14 times more likely and 3 degrees hotter. Oh yeah, your risk for fires has also gone up.
I'm running out of time, so let me just quickly go
Heat waves?
forward, just play another video too. This one every fall, I think this is a very cool way to show people what's going on around them. I mean, it's somewhat harmless because we're talking about fall leaves, but I'll quickly say this.
Fall is here. Maybe? If you're wondering where the yellow, red, and orange fall leaves are near you, the delay might be because of the weather. The timing and quality of the colors depends on a combination of temperature, precipitation, and sunlight. During the day, the leaves use sunlight to produce sugars. Cooler nights trap these sugars in the leaf. These sugars lead to the production of pigments, which produce our fun fall foliage. The best fall displays occur after sunshine-filled days, cooler nights, and a healthy dose of rain in the summer. But when summer heat extends longer into the fall, that warmth can degrade the pigments and delay peak color.
So there I explained the weather part of it, of how day to day you can see if it's going to be
here. Maybe?
If it's going to be happening on that day. But then overall, we have to talk about the climate change trend of summer temperatures extending more into the fall, which is pushing back fall season, fall leaf color changing season. And then, oh, I don't need to show this. And lastly, I mean, I think it's important to show that, you know, we talk about weather, climate change, and all the effects of it. But I think a really important part of our climate team at the Post is it's pretty multifaceted, that we also talk about the climate solutions and what you can do. Some of it's on a policy level, some of it's just as clear as like, which toilet paper should you use? We did a test of like really sustainable ones and not so sustainable ones. We also have one about using a bidet. These are from my colleagues. And then why you should eat lentils every day because they're very sustainable and they're good for you. And then also just like kind of a silly thing.
What is your favorite time?
Going out on the street and literally talking to people about how it affects them. And this one was just a silly thing we did about their dating lives just to get people interested in what they say. So I'll play a quick 10-second clip and then we will wrap up. All right.
Decided to take to the streets to see how climate and weather are impacting the dating lives of whoever would talk to me.
He is a 10, but he doesn't believe in climate change.
Oh, 0, negative, like 5.
They would just be a stupid 10.
Oh gosh, that is rough. Probably a 4, actually.
At least a 4, and then I'd like to hear some reasons on that. Like, we need to talk this out, you know, like, where does he land on the moon landing?
There are 2, but they compost.
Composting is cool. My roommate just got into composting, and she's been teaching me a little bit about that.
Do you want to date your roommate?
I do not. No.
He is.
So that's just to give you a little bit about, you know, the different types of coverage that we do and the message that we're trying to show appropriately, as well as some more fun things that we do just to engage people on climate change. So thanks so much.
Boy, thank you, Kasha. What fun. You know, just to go from a scientist who is now a professor and doing all these other things, and then, you know, hear from our applications coordinator and hear some of the cool kind of very modern and futuristic ways in which these data are being used, and then to go and hear from one of our former GPM outreach members and you know, how she's kind of taking what she did already and then expanding upon it is just amazing. So I hope you are as amazed as I am. And you know what I'm going to do? I am going to hold off on our final speaker and give you a preview of coming attractions, because on June, let me check to make sure I get this right, on June 13th, we're going to be focusing on precipitation extremes and also the ways in which we can take a look at things that have happened in the past, present, possibly in the future, and help people who are in various places understand how NASA is studying this. And also, as was asked in the chat by a couple of people, how do we help different audiences to understand this, to not be terrified and afraid, but to understand that these are data. This information is helping us to better understand our home planet, and then also to make decisions, to make choices, to figure out how to move forward. So I am going to save my dear Dr. Genevieve de Messier for our next webinar, and that way we will finish on time, and she will not have to rush, because the cool information that she's going to share with us is just wonderful. So I am going to put in our chat box one more time the site that you're going to go to see the story map. And in that story map, what you're going to find is at a couple of days, this recorded webinar, you're going to find many, many more links to get more information about the cool things Dr. Marshall Shepard is doing, the talks that he has, the ways in which he's helping to reach to get people to understand the impact on underserved communities of climate change. You'll be able to understand a little more about the Earth to Sky programs, so that'll give you a taste of coming attractions. You'll also learn a little bit more about Kasha's work, as well as seeing some of her articles with the Washington Post, and seeing a couple of her comedy routines. And you'll be able to see some of the work that Andrea and I have done in differentiating weather and climate and creating a suite of different materials. And these materials include one-pagers that help people understand the differences and similarities in predicting weather and in forecasting weather and all the variables that are involved in that, and in understanding climate, because really being able to differentiate between those two is super important. It is important because sometimes people will say, man, you're saying the climate's changing, and yet weather forecasters, they can't even tell if it's going to rain or snow in the next 4 days. So but the problem is when people are misunderstanding those differences, weather is what you're going to wear right now. So as Dr. Shepard said at the beginning of this webinar, boy, are you lucky, because right now, while you are here in Georgia, even though climatically it should be a lot hotter, actually there's a nice cool front coming in. So for the next 3 days while I'm here, we're going to be able to enjoy really cool weather. For me, in looking ahead at the weather forecast, I brought an umbrella, I brought a light jacket, and I brought short sleeve shirts, and I even went ahead and brought a swimming suit, because, you know, hey, who knows? That is the weather. Climate tells me what I have in my closet. Weather is what I wear today, what I keep in my car. Climate is kind of like, do I have still some long sleeve shirts because it may be a little cool in the evening? Do I keep that light jacket with me? Or do I put that away until next fall? So weather and climate, super important to understand the similarities, but even more important, the differences, because that really helps people to understand why we are able to, with so much more accuracy, look at the weather and do these, look at the climate and do these climate models, because basically climate entails looking at the past 30 years or more of weather, and then looking for those patterns and trends. And patterns and trends is all about what we do in science. So I hope this all tastes like more to you, that you'll just get into that story map and have fun with it. You don't have to read everything in there, just flip around and read what interests you. If you read something and you say, oh, wow, this is too cool, I want to learn more, get in there, learn more. Go to some of those NASA sites that I put in there, that climate change site. Oh my goodness, you get in there and learn about the ways in which they're using vital signs to help us understand how we can determine whether or not our Earth systems are healthy. it's just amazing. And there's so much information there to look at. So thank you so much to Dr. Shepherd, who had to run. Thank you so much to Andrea. Thank you to Kasha. Thank you, Genevieve, who so kindly does not mind going next month instead of this month. And to our dear Chris, who hung in there through it all, just in case he was pulled to come and give us a little more information. And really, claps to all of you. It just makes it gives us so much hope and so much gratitude to know that the work that we care so much about and that we take so seriously matters to you as well. And so with that, we can stop the recording.